So, as my intro suggested, my name is Mimi, or Pippi. Today I'm going to be giving a presentation I like to call Peering into the Abyss. When I first developed this talk, it was an hour long, and we didn't want to make you wait around that long, so I've condensed it. But that means we are just touching the surface on some of these really exciting topics. So if you have questions, please hold them to the end. I'll try to answer as many as possible. My talk today is going to cover three main areas. One is a little bit about myself, how I got working into telescope operation and got involved with these very large collaborative projects, such as the Event Horizon Telescope, that helped us take the first picture ever of a black hole, released back in 2019. Yeah, it's really fucking exciting. If you Google a picture of black hole, we now have an image with telescopes that we created. It is a very, very exciting time to be studying astronomy. I'm also going to give a very brief and horribly rough overview of black holes, and then we'll talk a little bit about the Event Horizon Telescope and how over the last decade, how over the last 20 years, we've really pioneered new techniques in order to observe these very mysterious objects. It's a really exciting time to be alive if you're excited about space and the cosmos. We're really in this golden age of astronomy where our technology has finally caught up with our theory and we are able to discover things previously unimaginable. And the topic we have today of black holes is ones that we've been talking about for 100 years. And so I hope that you guys can help me come together and kind of appreciate the moment we're at today and our ability in order to understand the universe we live in. So I'm going to give you just a little bit of brief about me. I have my bachelor's in science and astrophysics. I have my master's in systems engineering. I'm working on another master's in environmental engineering that I'll be done with by the end of the year. So I'm by no means an expert on black holes, but I have had the very good fortune to work at facilities that have taken some of the most spectacular observations of these mysterious objects. So for 5 years, I worked for the Maunakea Observatories. Mauna Kea is a 14,000-foot volcano, dormant, that lives on the Big Island of Hawaii. And it is one of the most incredible places to observe the night sky. We'll talk about why that is in just a moment. But I worked on two facilities there. One was the Smithsonian Astrophysical Observatory Submillimeter Array. That's this one here. It's a lot of little baby dishes. And then also the James Clerk Maxwell Telescope. That's one big daddy telescope right here. That's 15 meters across. I had the privilege of getting to work in telescope operation on a day-to-day basis. I'd go up for about a week at a time, acclimatize to the 14,000-foot elevation difference, and then spend the next 5 or 6 nights working with visiting scientists who have previously gotten their cutting-edge experiments approved by both scientists internal to our organizations and external experts. And they finally get a chance to come take the pictures. So they come to me, we talk about the kind of observations they need, at what time their object, maybe it's a black hole, maybe it's a star-forming region, maybe it's a nebula of some sort. We'll come together, we'll look at when it's going to observe and set in the sky, we'll talk about the types of images they want, the filters they want, then we'll work together over the course of the next couple of days. Hopefully the weather cooperates, as it often does in the very, very dry peak of Mauna Kea. And then they get to take home some really excellent raw data that hopefully will push forth our envelope of understanding. I love looking at this image of Mauna Kea. I hope everyone can take a look. Over here we have some of those powerful telescopes in the world, the two twin Keck domes, each 10 meters across. We also have the Subaru telescope. And you can see a few things here that I love about Mauna Kea. First is that you are above the clouds. You know, we're at 14,000 feet, all right? You are way above the moisture levels, which means that you can get perfectly crisp, clear images of the cosmos. You know, if you have water vapor in the air, if you have extra layers of the atmosphere, the lower atmosphere, if you're maybe at sea level, you know, that air really adds scattering effects to your images. If you want a crisp, clean image, you got to go to the clearest place in the world. That's Mauna Kea. But also, you can see there's a little bit of snow here, right? Mauna Kea in Native Hawaiian, of course, means white mountain. And when they started building the telescopes, they needed a snow plow. They ordered one for the mountain, and it didn't come. And they ordered another one, and it didn't come. And finally, they called it the company, and it was like, oh, we thought someone was pranking us, needing a snow plow in Hawaii. But we are that high up that it snows quite often, which adds this extra layer of complexity to the sensitive instruments we have. Okay, this next visual, hopefully it won't make you feel a little dizzy. It's a video that my good friend Will took. I'm hoping it'll just start. And what it shows is essentially my commute to work. We start at 10,000 feet. We start actually, this is at 7,000 feet. You can see the fog rolling over the mountain. Over here are some of the telescopes, just little dots over on the peaks. You have to drive up the mountain, you go off-road a little bit, and then you're going to end up at the very top of the summit. I'm gonna...
When you drive in, what do you to your right?
The one to my right? Oh, okay. Thank you, guys. I appreciate the supportive crowd. You know, this is a give and take, this talk, right? So we all do it together. So this is me leaving work. This is my friend Will taking this. But I feel, Mauna Kea is one of the most special places in the world. A lot of people feel this way. If you look at some traditional Hawaiian creation stories, Mauna Kea is the kumalipo. It's the belly button, the umbilical cord between the heavens and earth. And that's something that I felt being there every day. I really feel like it's one of the most special places on Earth. There's actually an incredible formation combined from the lava and the ice create very, very hard rock that people who lived here a long time ago would actually use to create tools. So there's a cool ice age reserve. Across the way on Mauna Loa, we've been taking observations of carbon dioxide in the atmosphere since the 50s. If you ever see a Keeling curve, looking at that very scary curve about our carbon dioxide situation with climate, started on Mauna Loa. This is really Science Island. It's not just the observatories, it's not just the telescopes. There's a lot of science that happens in this very, very special place. As you can see, we're getting above the clouds here. You get the most incredible sunrises and sunsets. You got to work 14 hours, but you start the night at 5 p.m., you set the telescope up, you see a great sunset, you have a great sunrise, you close up the dome at 7 a.m., and there you go. This is the facility that I worked at most recently. It's the giant toilet paper roll on its end. But this is the James Clerk Maxwell telescope. And there's a lot of observations going on at any given time, right? There's not a lot of telescopes in the world that have the ability to pierce through water vapor at the wavelengths we observed at. We're at this very sweet spot in between optical telescopes and radio telescopes. It's called submillimeter astronomy, which refers to the literal wavelength of light. It's also 230 gigahertz if you guys are radio people and want to think about it in the frequency space. But in order to observe at these wavelengths, you need to have a few things, all right? One, you need to have super, super cold instruments, all right? The coldest place in the known universe is actually inside that dome we just saw, because we keep our instruments at 700 millikelvin above absolute zero. That's more than 450 degrees below 0 Fahrenheit, because we need to have very, very sensitive electronic devices that amplify these submillimeter frequencies in order for us to be able to record them. And we didn't have that technology till the 70s, so this is really the final frontier of astronomy that we're talking about. But you might notice something as you see this dish whirl around, all right? These are all submillimeter telescopes, which means they don't have traditional glass. Do you see this giant membrane here? What you're looking at is actually the world's second largest single sheet of Gore-Tex that covers our main dish, because even though light as we know it, light that our eyes are sensitive to, right, is not able to pierce Gore-Tex, very long wavelengths, submillimeter frequencies, easily can pierce through. We have the world's largest sheet of Gore-Tex stashed in the cupboard just in case we rip the one we have on. Just always good to have backup. So you can see a really beautiful night sky. We're constantly rotating throughout the night. You'll see this at our very own dome here on Playa. If you want to be able to observe different things in the night sky, you got to rotate the dome. For time's sake, I'm going to speed this up a little bit and point out just a few details. Something that you might see, and something that was talked about, I think, in Nathaniel's presentation, was this use of artificial stars, right? How can we use lasers in order to create an artificial star that we can use to improve our observations? Oh. All right, there we go. You might see some guide stars, like giant laser beams or lightsabers in the background. Ooh. All right, we'll see if it cooperates with me getting to fast forward a little bit. It looks like it just started over, which is what I was not hoping for. But I can show you in this next image here. I really wanted to get you to see the like day-to-day activities of what we're doing, because at the end of the day, if something goes wrong with this telescope, it's precious time, and you very quickly have to start going into triage mode, which means trying to figure out if something has wrong with the optical system, with your cryogenic system, your electronic, your software system. Are you pointing at the wrong object? Did you put your coordinates in wrong because you're a dummy? Did you write down the wrong time for sunrise or sunset or star rise, star set? Things like this that might trip you up. But this is what it looks like in the control room. You have, there's a few more monitors out here, but it's about 16 monitors to control the telescope. Here's me with one of the tertiary mirrors. Here's one with me with the big dish, a little sunset, me hanging out with all my pals. You can't do science alone. And of course, this image that really is the focus of this talk. We got a little sidetracked, but the focus of the talk is this picture right here. Have any of you seen this picture before, this glowy donut? Would you guys have recognized that as a black hole? Yeah, okay. You know, maybe yes, maybe no. I mean, it's a really new image. It only came out in 2019. So let's talk a little bit more about how we got there. I mentioned I worked on sub-millimeter telescopes. I mentioned that there's a wavelength of light. So let's take a step back and think about what that means, right? Some of us might be familiar with the electromagnetic spectrum. Things on Earth, things in space are constantly absorbing and giving off energy at a variety of frequencies or wavelengths. Same difference. Our eyes are only sensitive to a small rainbow of them, which means there's light all around us that has incredible information that we can use to understand the cosmos. But we need to develop special devices, right? Much better eyes for our telescopes in order to be able to process it. So I love looking at this image of the Whirlpool galaxy. It's one of my favorite. It's what we call a starburst galaxy. So if you look at the corner here, here's the Hubble image. We have a nice spiral galaxy similar to our Milky Way right here. And we have a spherical galaxy here colliding with it. That collision activates star formation at an incredible rate. 10, 100, maybe even 1,000 times on some of these spiral arms. And so if you're a scientist interested in star formation, like many of the scientists I work with, that's a really good place to learn about the universe and a lot of these basic mechanisms of cosmic life. So this is Hubble. This is kind of what our eyes see. If you start looking at more energetic regions, all right, you're going to start to see in ultraviolet, you're going to see hotter stars, bigger stars. You can go all the way to X-ray to see some of the hottest regions of space where atoms are atomized. But if you go back from where we're the optical, here's infrared. You guys look like a heat map. You know, we're looking, you can see all of the red M dwarfs, the tiny stars that make up about 70% of the stars in our Milky Way. But here, this is my baby, the radio image. I love a good radio image. Compared to Hubble, might look like a sneeze, but it's a pretty sexy one. This is where we can actually start seeing carbon monoxide and molecular hydrogen in order to understand how stars form, how planets form. I like to think about it as the cosmic wombs wavelengths. You know, we see the planets and the stars in the process of forming before they undergo fusion to give off heat and light in wavelengths we can see. Okay, so we're talking about radio wavelengths. Why do we use those to observe black holes? It has to do with the nature of where black holes live. These supermassive ones we're imaging with the Event Horizon Telescope live at the center of galaxies, where there's a lot of stars that are already giving off heat and light in visible wavelengths. If we can use these radio wavelengths, these sub-millimeter frequencies, you know, these are telescopes that are superb at studying the cold dust and gas of the universe. And we are able to pierce through a lot of that light that you just cannot do in an infrared or ultraviolet or traditional optical telescope. So there's no glass mirrors. They look like satellite dishes, but they're my babies. I'm a fangirl of the dishes. What can I say? Though we do, of course, have some glass dishes inside with some of the smaller components of the system. So black holes, they get a bad rep. You know, kind of like these vacuum cleaners that suck everything up through space. And it's really hard to start to conceptualize them because it's a not intuitive topic. So I really like to think about it as a whirlpool, right? It's not like black holes are moving through space, sucking things up. There's absolutely an event horizon, an edge, similar as if you were in a boat in this water whirlpool, where if you cross it, it's the point of no return, right? That is the region of a black hole where gravity is so strong that not even light can escape. But if you are past that edge, what we've called the event horizon, you're totally fine. Of course, if you're going into the black hole, you'll have this crazy time dilation, spaghettification. We can talk about that later if you want. I mentioned at the beginning of the talk that we have been theorizing about black holes since the time of Einstein, all right, the 1920s. So how do black holes get made? Where do they come from? If we're talking about black holes that are the mass of our own sun, or on the order of mass of our own sun, they're almost always going to form out of the cataclysmic death of a star, all right? Stars, just like humans, have lifetimes. They're going to grow up. They're going to burn their fuel. I know I just said stars are like humans, but you can bear with me. I sometimes think about stars as automobiles. Okay, you have your gas-guzzling Hummer O-type stars. These have lifetimes of like nothing, all right? They're so fuel inefficient. They burn and burn and burn, and they have lifetimes of 100,000 years. But also you have like your Volkswagen Beetles. They're like tiny and compact, and they last forever. These are your small M-dwarfs, and they have lifetimes longer than the age of the universe. I know we're talking, trillions of a trillion years. So they're going to have different life processes, as you might imagine. But mostly they're going to go through their hydrogen, they're going to go through their helium, they're going to go through this red giant phase. That they're several times the mass of our own sun, they'll be a red supergiant. And stars like our own sun are going to have a wimpy death. They're going to like puff up, and then they're going to collapse, and so outer layers are going to wisp off, all right? And you'll get them to be like a dense core. But if you're a big boy, if you are a few times, the mass of our own sun, maybe a little bit more than that, you have the chance to go supernova at the end of your life. So you burn through your hydrogen, and you burn through your helium, and then you start to have this kind of puffy phase, all right? Your midlife, end-of-life crisis, all right? You go through the red supergiant phase, and then when you collapse, you undergo supernova, right? Which is one of the most exciting phenomena we know in nature, where we're going to have an explosion where the outer layers of this star, this dying star, is going to be ejected at unfathomably high speeds, and the inner core is going to condense in potentially a black hole. These are the size black holes that Einstein theorized about. These are like similar to the mass of our own sun. But that's not the picture you saw. That is not the picture of that red glowy donut, all right? That's a super fucking massive black hole, all right? When you see those pictures, that's a black hole that's million or billion times the mass of our own sun. We still don't really know how they form. In fact, we didn't know they existed really until the 90s, and we started doing some more observations of them. So the hard thing about black holes is that you can't see them, right? That's like their whole shtick, right? Is that gravity is so strong, not even light can escape. How do you take a picture of it? It feels like I'm going to set up into a bad joke. So you have to get creative. And something that I love about astronomy and approaches to studying the cosmos is it asks you to be incredibly creative. And scientists throughout time, even with much more rudimentary tools, have really come up with novel ways to study these mysterious objects. So I'm going to show you, I just got so excited, guys. All right, this is what I wanted to show you. I don't know if you can see this. Hold on, I think I might need to play it. Hold on. All right, I'll set you up before I play it, all right? Do you guys see how there's just like a bunch of fuzzy dots? Okay. Up here is your scale, 10 light days. For reference, between us and the moon is 1.5 light seconds. Between us and like Pluto's 30 light minutes or something. So this is 10 light days. That's big. Here's years of observations, all right? This team of astronomers came back over the course of a decade and took pictures. Did I hit something? All right, cool. They took pictures over the course of many years, so that's something to be noted, all right? Well, we can play it twice, but just take a look at what's happening, all right? Maybe not? Anyone who has a little more technical skills than I do want to take a look at this? I thought I tried it out earlier today. If not, whatever.
I like your skirt.
Thank you. All right. What you would see here is stars around a supermassive black hole starting to wobble around in a weird way. In a way that suggests that there's not just a star nearby, but a giant black hole that is making these stars boomerang the center of their mass of the system. So here's a visualization of that same system. It was taken by Andrea Gaze and her team at UCLA. They're absolutely phenomenal. They use the Keck telescopes in Hawaii. And you can see that there's this crux point here. All right, this is the location of the supermassive black hole. This is the orbit of the objects around them, right? So this is how we used to have to study these supermassive black holes. We had to observe the way it impacted, had an effect on nearby objects and its surrounding environment. But That's changed recently. And here's the very nice background system. It's quite beautiful, as most things are in astronomical research. So we theorized about black holes in the 1920s. We first discovered a black hole and observed its surrounding effects in 1967, similar to that image with like a binary system that was moving and there was like a ghost mass, and they figured it out as a black hole. But in 2017, the first ever picture of the edge, the event horizon, was taken with a collaborative called the Event Horizon Telescope. Now, the way this works is a technique called interferometry. Essentially, the issue that we have with building a really, really good telescope to take a picture of a black hole is that you need incredible resolution, all right? Resolution equivalent to being here on the playa and looking up at the moon and being able to spot a single grapefruit or a mango or a watermelon or like whatever you want to call it, all right? A single piece of fruit on the moon. That is not resolution that we've had in previous astronomical imagery, and no one telescope can do it. Because like all optical objects, we are bound by this resolution limit, which is based on the size of the aperture and the wavelength of light we're observing. So we had to get creative, right? One of the beautiful things about astronomy is our ingenuity, right? And so what we did is we linked up telescopes all around the world. So if you can see in this image here, there's telescopes in the South Pole, in Chile, in Hawaii, all throughout North America and Eastern Europe. We would go further, but as the Earth rotates, you can only see the black hole for a certain period, so you can't have people on the other side of the Earth taking the same picture. And they first tried this back in 2008 with 3 stations in Hawaii and throughout North America, and it was like, no, we need better telescopes, we need more stations, we need better software. But now we all took a picture. For 10 days in April 2017, we pointed at supermassive black holes all throughout the night. We took our data and stored it manually. It's like a terabyte a night. It's a lot of data. We ship it to a supercomputer at MIT Haystack over in Massachusetts. And then many brilliant computer scientists and physicists and astronomers and image processors and software developers work together to develop that image that we know. So to give you an idea of just how many people this took, all right, this is like people who were board institutions, their telescopes were primarily involved. Here we have even more people who were involved, who helped funded it. Here we have even more people who had scientists who were affiliated with it. It was like hundreds and hundreds of authors on these papers that went out. This is what we expected to see. How many of you have seen, oh my gosh, what's the movie? Interstellar. How many of you seen Interstellar? It looks kind of like that, right? Right, and this is a simulation, and this is what we thought we would see. You see this ring of light, it has a glowy disc. It has a little bit of this crescent effect because of the way that it's rotating. So things moving away from us will be red shifted, things moving towards us will be blue shifted, giving that slight discoloration. The science team that put forth the Event Horizon Telescope produced these images. I really love these. So over here on the far left, we have the model of the simulation of what we thought we'd see. Over here in the middle panel, we have what we think the image of the black hole would look like if we had 7 telescopes, in this interferometric pattern. The more telescopes we have, the further apart we can pull them, the better resolution, the better the final image will be. And here's what it would look like with 13 telescopes. So you can really see a clear difference between adding more scopes. We always want more dish. And this is the image that we ended up with. It's pretty phenomenal. At this time, we took 2 images. We took one of Sagittarius A star in the Sagittarius constellation and one of Messier 87. Sagittarius A star was released much later because it's a more complicated image to reduce and clean up for various reasons. But we confirmed these ideas that were put forth by Einstein. It took us 100 years, but we finally were able to do this. And that's a really incredible achievement, not just for a single telescope or a collaboration, but also just within the realm of human history, of what we'll be able to build upon, as we come forth past one another. One of the ways that we felt very secure about the image that was produced by the Event Horizon Telescope was that 3 teams were split up. They weren't allowed to talk to each other or compare notes, and they used 3 slightly different image processes. So here's the 3 different image processes. They're quite similar. We took 10 nights of observations with 5 really good nights of data, and here's images from different nights from April 5th to April 11th. They all look very, very similar. This gives us more confidence in the image we produced. This is an image that just shows as we add more telescopes to this Event Horizon Telescope collaboration, how the image of the black hole changes. And so you can start to see, as we add more unique distances, add more locations, add more scopes, we start to get a much better image, more circular, much prettier. One of the really special things about being in Hawaii and working for the Maunakea Observatories is we're continuing a tradition of Hawaiian stargazing. You know, they have been some of the most incredible stargazers from their techniques in Polynesian navigation, and it feels very appropriate, for some people at least, to have some of these telescopes in the islands of Hawaii. There's a committee called Ahuahea Noa, and they are led by Uncle Larry Kimura. He was really the father of the Hawaiian language renaissance that occurred in the early 1970s to popularize the language after so many years where it was really put down. It was illegal, you know, for some time in the state. And so he helps head this program that comes up with unique Hawaiian names when there's an object discovered in Hawaii by one of the Hawaiian telescopes. And so he bestowed this name of Povehi onto this black hole, which means embellished, fathomless, dark creation. And it comes from Po, which comes from the Kumalipo, which is this creation chant. And Po is this source of never-ending creation. And there's something quite apt about that. It's a black hole that sucks in matter and maybe burps out these kinds of jets to be able to have such a fitting tribute in Hawaiian. We're getting to the end of the time. I'll show you a couple last images before I head out. Here are the two images that are probably most well known by the project. We have Sagittarius A star over here, Messier 87 over here. You can see slightly different scale where the sun's diameter here, Sagittarius A star is much smaller. There is about 1,000 solar mass difference. And over here, I like thinking about this. Here's our solar system. Here's Pluto. Here's where Voyager is, just to get an idea of the scale. We're also taking really pretty pictures, high resolution of their jets, those burps, once they're gobbling up matter and then they kind of burp out along the jets, getting really great shots of that. And that's it, guys. Thank you so much for sharing the space with me today, for listening to me talk and go on about astronomy.